Alright, in this video we're going to discuss section 8C, dealing with real population growth. Okay, now perhaps the most important application of exponential growth concerns human population. Okay, now we did talk about exponential growth in the last video, section 8B. You might want to review that video if you're not familiar with it. Okay, so here we're going to be using that in human population, like in example 1. Use an annual growth rate of 0.6% in a 40-year period for a certain population to find the approximate doubling time and then predict the population in 2050 based on the 2000 population of 6 billion. Okay? So now, in this case, we're going to have to use that approximate doubling time that we talked about in the last video. Now, if you recall the approximate doubling time formula, that's T sub double. That's going to be approximately equal to 70 divided by P. Now, this only works when your rate is less than 15%. Okay? Now, your P is the percent as it is, which is 0.6. So we're going to do 70 divided by 0.6 and come up with our approximate value here. So 70, let me clear this out, 70 divided by 0.6. If we round to the nearest whole number, it's going to be approximately 117. So the approximate doubling time would be 117 years. Okay? And now we're going to predict the population in 2050. Okay? Now, we're given 2050, and we're basing this on the 2000 population. So we need to find out what lowercase t is. T is, of course, the time. So 2050 minus the year 2000 would be 50. So our time is going to be 50 years. The initial value now this is based on a 2000 population of 6 billion. So 6.0 will be the initial value. And our answer will be in billions, so I'm using only 6.0. Now that formula we talked about in the last video for exponential growth is this. The new value is equal to the initial value multiplied by 2 raised to the lowercase t divided by t sub double. Now the initial value was 6.0 multiplied by 2 raised to the t, that's 50, divided by t sub double. We found that out to be 117. Now this we can type in the calculator. So I'm going to do 6.0 times 2, and then there's a hash key for your exponent. That's a hash key for your exponent. And then 50 divided by 117. And then hit enter. Now here we're going to round to the nearest tenth, or to the nearest to 1 decimal place. This will be approximately 8.1. And it's going to be 8.1 billion. So the approximate population in the year 2050 would be 8.1 billion. Okay. Okay, now let's look at another example of this. Okay. Here's another example. Use an annual growth rate of 1.1% in a 10-year period for a certain population to find the approximate doubling time and then predict the population in 2050 based on a 2000 population of 3 billion. Okay, so now we need the approximate doubling time. Which is that formula of T sub double. That's going to be approximately equal to 70 divided by P. And in this case, we're going to do 70 divided by the percent as is, which is 1.1. So on the calculator, we'll do 70 divided by 1.1. You'll get approximately, to the nearest whole number is going to be approximately 64. So here, the doubling time will be approximately 64 years. Okay. And now, let's find the approximate population in 2050. Well, T, to find that out, will be 2050 minus the 2000 population. Well, 2000 from 2050 will give you 50. So T is going to be 50 years. And also, your initial value, which was the 2000 population, that's going to be 3.0 billion. We're going to use 3.0 here. So now, the new value is, of course, the initial value multiplied by 2 times lowercase t, well, 2 raised to the lowercase t divided by t sub double. So now that initial value was 3.0 times 2 to the t, which is 50, over your t sub double, 64. So here in this case, this will be 3.0 times 2, and then the half key for your exponent, 50 divided by 64. And that's going to be rounded to the nearest whole, to 1 decimal places. This will be 5.2, approximately. So we're going to have 5.2 billion for the approximate population in the year 2050. Okay. Okay, now, next we'll talk about this question. What determines growth rate? What determines growth rate? The world population growth rate is the difference between the birth rate and the death rate. Okay? It's just a simple formula. We subtract the birth rate minus the death rate to get the growth rate. So like in example 3. The following table gives the birth and death rates for 4 countries in 3 different years. Find the net growth rate due to the births and deaths in each of the 3 years for country A. Based on these trends, predict how the country's population will change in the next 20 years. Okay, so here we're only going to be dealing with country A in this example. That's its first row. Okay. So now, the country A's net growth rate in 1985 was how many per 1,000? Well, in this case here, we look at the birth rate in 1985 and the death rate in 1985 and subtract those two using this formula right here. Okay? In 1985, the birth rate was 14.8 minus the death rate, in this case, is 11.8. So if we subtract 11.8 from 14.8, we're going to end up with 3.0. And here they want this as an integer, so we'll just say just 3. So the net growth rate in 1985 for country A was 3 per 1,000. Now what about the net growth rate in 1995. In 1995, for country A, the birth rate was 10.1 minus the death rate in 1995 for country A, it was 11.4. So if we do 10.1 minus 11.4, you're going to end up with negative 1.3. Yeah, you're going to end up with a negative number here because it's birth rate minus the death rate. And it can end up being negative. Now what about for 2003 for country A? For country A, the 2003 birth rate was 9.6. And in 2003, for country A, the death rate was 11.1. So it'll be minus 11.1. If we subtract 11.1 from 9.6, we're going to end up with a negative 1.5. So, country A's net growth rate in 2003 was negative 1.5 per 1,000. Okay? And now we're going to choose the best prediction about country A's future population based on the general trends in these 3 years. And by looking at this pattern right here, we're seeing that the population is decreasing. Because it's going from 3 down to negative 1.3 down to negative 1.5. So, the country's population here will decrease based on those general trends here. Okay, let's look at this next example, similar to net growth rate. The following table gives birth and death rates for 4 countries in 3 different years. Find the net growth rate due to births and deaths in each of the 3 years for country C. And based on these trends, predict how the country's population will change in the next 20 years. Okay, so now we're looking at country C. That's the 3rd row right here, as you can see. Now we want the net growth rate in 1985 for country C. That's always the birth rate minus the death rate. Okay? So in country C, the birth rate in 1985 was 10.6. Now we're going to subtract from it the death rate in 1985 for country C. Country C, it is 11.6. So 10.6 minus 11.6 will end up being -1. So the net growth rate in 1985 for country C will be -1 per 1,000. Now, country C in 1995, the net growth rate, we find that out by looking at the birth rate in 1995 for country C. That's 11.4. Minus the death rate in 1995 for country C. That's 11.3. So 11.4 minus 11.3 would be 0.1. So country C's net growth rate in 1995 was 0.1 per 1,000. And then country C's net growth rate in 2003, well, let's go to country C. In 2003, the birth rate was 12.3 minus the death rate for country C in 2003 was 10.1. So 12.3 minus 10.1 would be 2.2. So country C's net growth rate in 2003 was 2.2 per 1,000. And now we're going to choose the best prediction about country C's future population based on the general trends in those 3 years. Here we can see that it is going to be on the increase because we're going from -1 to 0.1 to 2.2. So the country's population will increase. All right, next we'll talk about carrying capacity and real growth models. For any particular species in a given environment, the carrying capacity is the maximum sustainable population. That is, the largest population in the environment can support for extended periods of time. Okay, now one thing we can talk about is what they call logistic growth. And that is when the population is small relative to the carrying capacity, logistic growth is exponential with a fractional growth rate close to the base growth rate, which is going to be R. As the population approaches the carrying capacity, the logistic growth rate approaches 0. The fractional logistic growth rate of any particular time depends on the population at that time, the carrying capacity, and the base growth rate, which is R. And this is a formula for the logistic growth rate. That's equal to R times the quantity of 1 minus the population divided by its carrying capacity. Okay. Now the next page is a graph of what exponential and logistic growth is and how they're different. Now in the exponential case, the growth rate stays equal to R at all times. Okay, so here, if you look at this particular graph right here, this will be your exponential growth. And it stays the same at all times. However, in a logistic case, the growth rate starts off equal to R, and as time progresses, the growth rate becomes ever smaller than R until it finally reaches zero as the population levels out to the carrying capacity. Okay, so here, this is what that graph looks like. Because that dotted line that you see going across, that's their carrying capacity. Here it gets closer and closer and closer to the carrying capacity. Here your logistic growth levels, it levels off as the population approaches that carrying capacity. So that's the difference between exponential growth and logistic growth. Okay? Now let's look at example 5. In this case here, we want to consider a population that begins growing exponentially at a base rate of 4.3% per year and then follows a logistic growth pattern. If the carrying capacity is 69 million, find the actual fractional growth when the population is at 10 million, at 30 million, and at 50 million. Okay, so we're going to start by identifying that, well, what R is. That's your base rate of 4.3%. And we're going to leave that as a percent because when we find the fractional growth rate, it will be as a percent. Okay? And also we know our carrying capacity is 69 million. So the carrying capacity, that's 69 million. Okay. That's your carrying capacity here. Now we're going to find out what the actual fractional growth rate is when the population is at 10 million. So our population is going to be 10 million. So here, the formula for the logistic growth rate that's going to be equal to R multiplied by 1 minus the population divided by the carrying capacity. Here I'm just writing out the formula so that way you'll see what I'm doing here. Okay, now the R was 4.3%. So we just say 4.3 times the quantity, 1 minus, the population was 10 million, divided by the carrying capacity, which was 69 million. Now, as I simplify this, the millions in the numerator and the denominator divide out. Now, this I can do in the calculator. So here I'm going to have, let's clear this out, 4.3 times, and I'm going to put this in parentheses. So left parentheses, 1 minus 10 divided by 69, close parentheses. And then hit enter. Now we're going to round this off to 2 decimal places as indicated in the directions here. So that amount will be 3.68 million. 3.68%. So the fractional growth rate is about 3.68% when the population is 10 million. Okay. Now, what about when the population is 30 million? So here the population here will be 30 million. Now here we're going to still use the same logistic growth rate formula here. The R is still going to be 4.3% times, in parentheses, 1 minus. Now the population will change to 30 million divided by the carrying capacity is still 69 million. Okay. We still have a carrying capacity of 69 million. The base rate is still 4.3%, but only thing is changing is the population. This time 30 million. The millions divide out, and that I can type in to the calculator by doing this. 4.3 times, and then left parentheses, 1 minus 30 divided by 69, close parentheses. And to 2 decimal places again, this will be 2.43%. So the logistic growth rate will be 2.43% when the population is 30 million. Okay? And now finally, what would the fractional growth rate be when the population is 50 million? So here the population would be 50 million, and we want the logistic growth rate for that. We're still going to have the 4.3 for our base rate multiplied by the quantity 1 minus, this time the population 50 million divided by 69 million, which is still the carrying capacity. So now your millions divide out, and now we're going to do 4.3 times, and then left parentheses, 1 minus, this time 50 divided by 69, close parentheses. And to 2 decimal places, this will end up being 1.18%. Okay, so now the fractional growth rate is about 1.18% when the population is 50 million. Okay. All right, and finally in this video we'll talk about overshoot and collapse. The phenomenon where a real population increases beyond the carrying capacity in a relatively short period of time is overshoot. And if the overshoot is substantial, a rapid and severe decrease in the population can occur, which is a phenomenon known as collapse. So in this case, this graph that I'm going to outline in red indicates the overshoot and collapse. Here's the overshoot, goes way up, and then it falls drastically like this. That's what we mean by overshoot and collapse. Okay. Now in this case, let's talk about what is the carrying capacity. Okay. Any estimate of carrying capacity is subject to great uncertainty for at least four important reasons. One of them is that the carrying capacity depends upon consumption of resources such as energy. However, different countries consume at different rates. And then carrying capacity depends on assumptions about the environmental impact of the average person. A larger average impact on the environment means a lower carrying capacity. And then the carrying capacity can change with both human technology and the environment. And the Earth is such a complex system that precisely predicting the carrying capacity may be impossible. Okay. Now let's look at this final example for this section. Here we're going to use a growth rate of 1.2% to predict the population in 2052 of a country that in the year 2006 had a population of 100 million. And we're going to use the approximate doubling time formula. Okay. Now, let's find out what T sub double is going to be. And of course, that's this formula that we talked about earlier. 70 divided by P. That's the approximate doubling time formula. And this is going to be approximately equal to 70 divided by the growth rate as is 1.2%. So it'll be 70 divided by 1.2. So if I do 70 divided by 1.2, you'll get approximately, let's say, 58. So the approximate doubling time would be 58. And now we're going to find out what the predicted population of that country is in 2052. Now, we need to find out what our time is in years. That's T. So if I do 2052 minus, we were told that in the year 2006. So let's use that. Subtract 2006 from 2052, you're going to get a time of 46 years. 46 years is your T. The initial population, or the initial value, that's going to be 100 million. But in the formula, I'm only going to use the number 100. Okay? So now, the new value, to find that out, that's this formula. The new value will be the initial value. Initial value multiplied by 2 raised to the T divided by T sub double. Initial value is 100 multiplied by 2 raised to the T, that's 46, divided by T sub double, that's 58. And I guess I can do that on the calculator as well. So this is 100 multiplied by 2 raised to the 46 divided by 58. And to the nearest whole number, as they indicated in the directions, will be 173 million. Okay. So here, the predicted population of the country in 2052 will be 173 million. Alright. Now that will conclude this video on real population growth.